I'm going to discuss the simple harmonic motion kinematics equations. Okay? I'm not going to derive the simple harmonic motion kinematics equations. I'm just going to state them. All right, give me a minute to draw a picture of a system that undergoes simple harmonic motion. All right, I've drawn a picture of a simple harmonic system. In this case, I have an object attached to a spring. Okay, the object has a mass m. The spring has a spring constant k. I've also defined an x-axis such that the origin corresponds to the position for which the mass does not experience any force from the spring. Okay, so that's referred to as the equilibrium position. Okay, so for this system, I'm now going to state the kinematics equations. And it'll be useful to define a variable called omega. It looks like a W. And it's equal to 2 pi divided by the period of the system. Okay, the period is denoted by capital T. If you like, you can also think of omega as 2 pi times the frequency of the system, because the frequency, remember, is the reciprocal of the period. All right, so with that definition, we can state the value of x as a function of time. So it's going to equal the amplitude times a sine function. Okay. X sub max is what I'm calling the amplitude of the biggest value of x. Okay. And then we also can state the velocity as a function of time. So the velocity also, of course, has a maximum value, okay? And in this case, the maximum value, the Vmax, is related to the maximum value of x. It's equal to omega times x max, okay? And then finally, we have the expression, the equation for acceleration. That's equal to a max times the sine of omega t plus pi. Okay, so the acceleration and the x value, the x variable, they are not at their maximum values at the same point in time. Okay, so that's the effect of that pi there. Okay, now the A max the maximum acceleration, that's also related to the maximum value of x and v. Okay, so that's equal to omega v max, okay, which is equal to omega squared x max. Okay, and so there you have it. Now, I said that a simple harmonic system is a system in which a corresponding parameter is defined in terms of a sine or cosine function. Okay, that's also referred to as a sinusoidal function. So as you can see, x, v, and a are all simple harmonic. Okay? Now, let me just give some clues to how you can derive these formulas. So, the force due to a spring is equal to minus kx, where k is the spring constant, but it's also equal to ma, okay, if the spring is the only force applied to an object. All right. Now, if you know calculus, you might know that the acceleration is what's called the second derivative, and if you know what a differential equation is, you can identify what I just wrote as a differential equation. The solution to that differential equation is the equation that I wrote there for x. Okay? And the v and the a can be derived by taking derivatives of x. All right? If you didn't understand any of that, don't worry. Okay? But if you have had calculus and you're curious, you can look into that. Okay? So, we've got a function for x. We have x as a function of time. We have v as a function of time. And we have a as a function of time. Let me emphasize that these kinematic equations apply to all simple harmonic systems. Yes, you might have a different system that doesn't have a spring and doesn't have a mass. However, if it's simple harmonic, the kinematics equations will still be similar. You'll just change some variable names. All right? Now, there is a relation between the omega, let me put a box around that, and the spring constant and the mass, excuse me. Let me show you what that is. So, look at the formula that I wrote there. Minus kx equals ma. So, that says that minus k over m is equal to a over x. I just rearranged the terms in the equation. But we have an expression for a and x there in the boxes, don't we? So you can go ahead and make that substitution, and let's see what we get. So the acceleration is equal to a max times a sine function. Let me do the following. Let me replace a max with omega squared x max. Okay, and let me replace the sine of omega t plus pi. Let me replace that with minus sine omega t. Okay, convince yourself that by removing the pi, that's equivalent to multiplying the sine function by a minus 1. All right, and so I divide that by the expression for x, so x max sine omega t, and then you can see that we're going to get some cancellation. So the x's cancel, the sines cancel, and we have omega squared minus omega squared is equal to minus k over m. So that tells us that omega is equal to the square root of k over m. That's an important formula because using the definition of omega, you can relate the period and frequency to k and m. Okay? Now, let's use these expressions to analyze the energy of the system, the total energy. So, we know that the total energy is the kinetic energy plus the spring potential energy. Okay, and that's true for any point in time. So, replacing V and X with the equivalent formulas from the kinematics equations, we get 1/2 m times omega squared x max squared cosine. And so what I'm doing is I'm replacing V with the sinusoidal function that's equal to V for all time. Okay, there's that, and then 1/2 k, and then for x we have x squared is equal to x max squared times sine squared omega t. And now let's use what we just found that omega squared is equal to. So we just found out that omega squared is equal to k over m. Okay. Okay, and so we get some cancellation, don't we? So the m's cancel, and we have 1/2 k x max squared times cosine squared omega t plus sine squared omega t, but the cosine squared plus the sine squared with respect to any angle is always 1. Okay, so we can discard that parenthesis blob. And so what do we have? We have that the total energy is 1/2 k x max squared. Okay? Now, let me explain that. So, the same way that when a rock falls, it converts all of its potential to kinetic, okay? And if you throw a rock up into the air, it converts all of its kinetic to potential. In the mass spring system, you have a situation where the energy, at one point it's all spring potential energy, and then at another point it's all kinetic, and then in between, at other points, it's a combination of both, okay? When the object is at the maximum x value, okay, then for an instant, it's not moving. V is 0, and so you have no kinetic energy, and you have all spring potential energy, okay? That's at the extremes. Now, as the mass is rushing through the x equals 0 point, the equilibrium point, it's passing it at high speed, and it's going to overshoot, right? At that point, when x is 0, notice that it has no spring potential energy. At that point, because energy is conserved, we know that we've got all kinetic energy, and the kinetic energy is equal to the boxed expression. Okay, so all of that is to say that the total energy can also be found this way, by finding 1/2 mv max squared. Okay, that's equal to the total energy as well. Sometimes it's pure kinetic, sometimes it's pure kinetic energy, sometimes it's pure spring potential energy. It just converts back and forth. All right? Now, let's use all of this work to do a problem. Suppose I analyzed a mass spring system undergoing simple harmonic motion, and suppose I determined that the maximum deviation of equilibrium, in other words, x max, was equal to 5 centimeters. All right. Suppose that I also determined that the frequency was 10 hertz, and suppose that the object that's moving back and forth has a mass of 4 kilograms. Okay, so the question is, can we, from that information, that limited information, can we determine the maximum velocity, the spring constant, and the total energy? Okay, if you like, you can pause the video and take a shot at this. I'm going to work it out right now. So the Vmax is equal to omega times x max. That's equal to 2 pi times the frequency times x max, which is equal to 2 pi times 10 times 5 centimeters. And let me convert to meters. That was a trap. So 0.05 meters. And now let's simplify that. So let's see. 2 times 10 is 20. 0.05 is 5 divided by 100. And 20 times 5 divided by 100 is 1, because everything cancels. And so what do we have left? We have that the maximum velocity is pi meters per second. Okay? Now let's calculate the spring constant. So omega, remember, is equal to the square root of k over m. So that means that omega squared is equal to k over m. So k is equal to m times omega squared. And omega squared is equal to 2 pi times the frequency, that all those 3 pieces squared. Okay, and so now we can replace with numbers. So 4 times 2 pi times 10 squared. And let's see what that gives. So 4 times pi squared times 100. So that gives 1600 pi squared newtons per meter. All right, now what do we have left? The total energy. So that can be determined by 1/2 mv max squared, or 1/2 k x max squared. So I'll go ahead and use 1/2 k x max squared. So 1/2 times k, which is 1600 pi squared, times the 0.05, because we want to convert to meters, right? All right, so now let's simplify that. So 1/2 of 1600 is 800 pi squared, and then 0.05 squared That's equal to 5 over 100 times 5 over 100. Okay, so let's see, what can we do now? So 800 divided by 100 is 8. And 8 times 5 is 200. 200 divided by 100 is 2. Okay, and by the way, the pi should be squared. So putting it all together, what's left over, I have 2 pi squared joules. Okay? I got all of those parameters just using the kinematics equations and follow-on work. Okay? Now, let's have you try a similar problem. Suppose that I had a mass spring system such that the spring constant was 10 newtons per meter and the maximum velocity was 0.1 meters per second, and the object that was moving back and forth had a mass of 2 kilograms. Okay? Is it possible with that limited information to determine the amplitude of x, okay, as well as the period, as well as the total energy? Okay, so pause the video and work all that out now if you can. All right, so I will go ahead and work it out as well. So omega is equal to 2 pi times the frequency, which is equal to the square root of k over m. Therefore, the frequency is 1 over 2 pi times the square root of k over m. And therefore, the period is the reciprocal of that, or 2 pi times the square root of m over k. All right, so let's see what that gives. 2 pi times the square root of 2 over 10. So the square root of 1/5, so 2 pi over the square root of 5, or if you like, 2 pi root 5 over 5 seconds. All right, and let's do the total energy next. So we're going to use this formula to do it. 1/2 mv max squared. All right, we could use 1/2 kx max squared, but we don't know what x max is. Furthermore, how do we know we're not going to make a mistake? All right, so it's safer to just use what's given. So 1/2 times 2 times 0.1 squared, that's equal to 10 to the minus 2, or 0.1 joules. All right. Now we can use the total energy to find the value of x max, because we know that the total energy is equal to 1/2 k times x max squared. So that means that, let's see, x max squared is equal to 2 times the total energy divided by k. So x max is equal to the square root of 2 times the total energy divided by k, which is the square root of 2 times 0.01 divided by 10. Okay, and let's see what that gives. the square root of, if I multiply the top by 100, I get 2. If I multiply the bottom by 100, I get 1,000. So the square root 1 over the square root of 500, or the square root of 500 divided by 500, which the best I could do, let's see, 500 is equal to 100 times 5. Square root of 100 is 10, so 10 root 5 divided by 500. So root 5 over 50 joules, and I just barely fit that in there. Root 5 over 50 joules is as good as I could get it. Okay? So I hope that is what you got.